Welcome to our next lecture. Lecture with you, Doctor of Chemical Sciences, Associate Professor Ilhama Zarbaliyeva, Department Biophysical and Bioorganic Chemistry of Azerbaycan Medical University. Today we will talk about heterocyclic compounds, classification, properties, and important derivatives applicated in medicine, condensed heterocyclic compounds, and alkaloids. First of all, about heterocyclic compound. Heterocyclic compound, also called heterocycle, any of a major class of organic chemical compounds characterized by the fact that some or all of the atoms in their molecules are joined in rings containing at least one atom of an element other than carbon. The cycle part from Greek kaklos, meaning circle, of heterocyclic indicates that at least one ring structure is present in such a compound, while the prefix hetero from Greek heteros, meaning other or different, refers to the non-carbon atoms or heteroatoms in the ring. In their general structure, heterocyclic compounds resemble cyclic organic compounds that incorporate only carbon atoms in the rings. For example, cyclopropane with a 3-carbon atom ring, or benzene with a 6-carbon atom ring. But the presence of the heteroatoms gives heterocyclic compounds physical and chemical properties that are often quite distinct from those of their all-carbon ring analogues. Heterocyclic compounds include many of the biochemical material essential to life. For example, nucleic acid, the chemical substances that carry the genetic information controlling inheritance, consist of long chains of heterocyclic units held together by other types of materials. Many naturally occurring pigments, vitamins, and antibiotics are heterocyclic compounds, as are most hallucinogens. Modern society is dependent on synthetic heterocycles for use as drugs, pesticides, dyes, and plastics. Now about general aspects of heterocyclic compounds. The most common heterocycles are those having 5 or 6 membered rings and containing heteroatoms of nitrogen, oxygen, or sulfur. The best known of these simple heterocyclic compounds are pyridine, pyrrol, furan, and c.e.n. A molecule of pyridine contains a ring of 6 atoms, 5 carbon atoms, and 1 nitrogen atom. Pyrrol, furan, and c.e.n. molecules each contain 5 membered rings composed of 4 atoms of carbon and 1 atom of nitrogen, oxygen, or sulfur, respectively. Pyridine and pyrrol are both nitrogen heterocycles. Their molecules contain nitrogen atoms along with carbon atoms in the rings. The molecules of many biological materials consist in part of pyridine and pyrrol rings, and such materials yield small amounts of pyridine and pyrrol upon strong heating. In fact, both of these substances were discovered in the 1850 in an oily mixture formed by strong heating of bones. Today, pyridine and pyrrol are prepared by a synthetic reaction. Their chief commercial interest lies in their conversion to other substances, chiefly dyestuffs and drugs. Pyridine is used also as a solvent and waterproofing agent, a rubber additive, an alcohol denaturant, and a dyeing adjunct. Furan is an oxygen-containing heterocycle employed primarily for conversion to other substances, including pyrrol. For a close chemical relative of furan is obtained from odd hues and corncobs and is used in the production of intermediates for nylon. Cyanophane, a sulfur heterocycle, resembles benzene in its chemical and physical properties. Its frequent containment of the benzene obtained from natural sources and was first discovered during the purification of benzene. Like the other compounds, it's used primarily for conversions to other substances. Furan and cyanophane were both discovered in the later part of the 19th century. In general, the physical and chemical properties of heterocyclic compounds are best understood by comparing them with ordinary organic compounds that do not contain heteroatoms. Cyclic organic compounds containing in the ring one or more heteroatoms, nitrogen, oxygen, sulfur, are called heterocyclic compounds. Heterocyclics may be classified as saturated, unsaturated, and aromatic, as well as by the number of carbon and heteroatoms in the ring. The nature of heteroaromaticity. Aromaticity denotes the significant stabilization of a ring compound by a system of alternating single and double bonds called a cyclic conjugated system, in which 6p electrons generally participate. A nitrogen atom in a ring can carry a positive or a negative charge, or it can be in the natural atom. An oxygen or sulfur atom in a ring can either be in the neutral form or carry a positive charge. A fundamental distinction is usually made between those heteroatoms that participate in a circle conjugated system by means of a lone or unshared pair of electrons that are in an orbital perpendicular to the plane of the ring, and those heteroatoms that do so because they are connected to another atom by means of a double bond. An example of an atom of the first type is the nitrogen atom in Pyrrol, which is linked by single covalent bonds to two carbon atoms and one hydrogen atom. Nitrogen has an outermost shell of 5 electrons, 3 of which can enter into the 3 covalent bonds with other atoms. After the bonds are formed, as in the case of Pyrrol, there remains as an unshared electron pair can engage in cyclic conjugation. The aromatic sextet in Pyrrol, made up of 2 electrons from each of 2 carbon-carbon double bonds and the 2 electrons that compose the unshared electron pair of the nitrogen atoms. As a consequence, there tend to be a net flow of electron density from the nitrogen atom to be carbon atoms, as the nitrogen's electrons are drawn into the aromatic sextet. Alternatively, the Pyrrol molecule may be described as a resonance hybrid. That's a molecule whose true structure can only be approximated by 2 more different forms called resonance form. You see in this slide 5-membered heterocyclic with 1 heteroatoms: Pyrrol, furan, cyanophane, indole, and pyrazole, imidazole, thiazole, oxazole, benzimidazole. And orbital structure of Pyrrol, orbital structure of furan. Now about 5-membered heterocyclic introduction. The main reason for the study of Pyrrol came from the work on the structure of the blue respiratory pigment and the chlorophyll, the green photosynthesis pigment of plants. Cyanogen does occur in plants in association with polyacetylenes, with which they are biogenetically closely linked. Furan occurs widely in secondary plant metabolites, especially in terpenoids. Unsubstituted pyrrole, furan, and cyanogen are usually obtained from petroleum. General characteristics: pyrrole, furan, and cyanogen are colorless liquids or boiling points 126 degree, 30 degree, and 84 degree respectively. Pyrrole has a relatively high boiling point as compared to furan and cyanogen. This is due to the presence of intermolecular hydrogen bonding in pyrrole. Structure and aromaticity. Pyrrole, furan, and cyanogen are aromatic because they fulfill the criteria for aromaticity. The extent of delocalization of the non-bonding electron pair is decisive for the aromaticity. Thus, the grading or aromaticity is in the order of furan, pyrrole, cyanogen, benzene. This order is consistent with the order of electronegativity values for oxygen 3.44, nitrogen 3.04, and cyanogen 2.56. And you see here orbital structure of pyrrole and orbital structure of furan. Now about structure and aromaticity, we will continue with these properties. They tend to react by electrophilic substitution due appearance of a charge on carbon atoms due to delocalization, as shown in the following resonance structure. Evidence of aromatic characters in pyrrole: all ring bonds are intermediate between single and double bonds. It tends to react by electrophilic substitution. Its exceptional lack of basicity and strong acidity as a secondary amine compared to the aliphatic analog pyridine. This can be explained on the basis of participation of nitrogen lone pair in aromatic sextet. See the previous resonance structure. Thus, the dipole moment of pyrrole compared with pyridine is reverted, and thus protonation occurs at carbon, not nitrogen. Now, synthesis of pyrrole. From 1.4 decarbonyl compounds, Pol-Nor synthesis. General substituting pyrrole may be synthesized through the cyclization of 1,4 decatones in combination with ammonia or amines. The ring closure is preceded by dehydration or condensation, which then yields the two double bonds and thus the aromatic P system. The formation of the energetically favorite aromatic system is one of the driving forces of the reaction, and this reaction called Pol-Nor synthesis reaction. Pyrrole is obtained by distillation of succinimide over zinc dust and by heating of a mixture of furan, ammonia, and steam over aluminium catalyst. Then by passing a mixture of acetylene and ammonia over a red hot tube. All these reaction synthesis called this synthesis of pyrrole. Then non-Pyrrol synthesis. This involves the condensation of alpha ammonia ketones with a beta decatone or beta ketoester to give a substituted Pyrrol. Now, acidic properties of Pyrrol. Due to participation of nitrogen lone pair in aromaticity, Pyrrol has exceptionally strong acidic properties. For a secondary amine, for instance, it can react with strong bases or Grignard reagents or potassium metal in inert solvents and with sodium amide in liquid ammonia to give salt-like compounds which can be used to alkylate or acylate the nitrogen atom as shown. Sensitivity of Pyrrol to acids. Pyrrol is sensitive to strong acids, and this is due to protonation occurs at one of C carbon 3, and the resulting protonated molecule will add to another unprotonated Pyrrol molecule. This continues to give Pyrrol trimer. This reaction is considered as an electrophilic addition to Pyrrol. Now, cycloaddition reaction. This reaction called Diels-Alder reaction. Cycloaddition reaction is one in which two reactants and together with formation of two new carbon-carbon bonds at the same time to give a cyclic product, Diels-Alder reaction. Diels-Alder's reaction involves addition of a compound containing a double or triple bond, 2p, and it's called dienophil. Across the 1,4 position of a conjugated system for PE13-diene with the formation of a 6-membered rings. The heterocyclic compounds can react as a 1,3-diene in a Diels-Alder reaction with reactive dinophiles, maleic anhydride or benzene, or with less reactive dinophiles in presence of catalyst. Now we continue cycloaddition reactions of Pyrrol, Diels-Alder reaction. You see here maleic anhydride, benzene, and acrylonitrile. The diene can be activated by the dienophile by AVG. Thus, N-alkyl Pyrrol and ammonia Pyrrol are more reactive than Pyrrol itself in Diels-Alder reaction, but less reactive than furan, the least aromatic 5-membered heterocycle, thus the most reactive in addition. The order of reactivity in Diels-Alder reaction is as follows, which is the reverse of aromaticity order. As expected for aromatic compounds, Pyrrol can react by electrophilic substitution. In comparison to benzene, Pyrrol is more reactive, thus the substitution is easier and milder reagents can be used. The increased reactivity is a result of resonance, which pushes the electrons from the nitrogen atom into the ring, making the carbon atoms of Pyrrol ring more electron-rich than in case of benzene. In fact, Pyrrol resembles the most reactive benzene derivatives, phenols and amines. See slide 4, resin structure of Pyrrol. Consequently, there are some modifications in usual electrophilic reagents. For instance, sulfonating and nitrating reagents have been modified to avoid the use of strong acid-induced polymerization. Also, reaction with halogens requires no Lewis acid. Reactivity in electrophilic substitution. Now, orientation of electrophilic substitution in Pyrrol. Electrophilic substitution normally occurs at the carbon atoms instead of at the nitrogen, as explained before. Also, it occurs preferentially at carbon 2, the position next to the heteroatom, rather than at carbon 3. If position second occupied, it occurs at position 3. This is due to attack at carbon 2 gives more stable intermediate is stabilized by a 3 resonance structure than the intermediate resulted from carbon 3 attack. It's stabilized by 2 resonance structure. Less stable. Now you see reaction, electrophilic substitution reactions of Pyrrol. An oxidation reaction of Pyrrol. Lysation of Pyrrol and nitrogen alkyl Pyrrol reaction shown here. And second electrophilic substitution, mono substitution, Pyrrol with electron withdrawing group, here is less reactive than Pyrrol, and incoming electrophilic directed to M position and position 4. Then monosubstituting Pyrrol with electron donating group, more reactive than Pyrrol, than here incoming electrophilic directed to P or O position, position 3 or 5. Then second electrophilic substitution, you see in this slide, in substituted Pyrrol with electron withdrawing group, incoming electrophilic directed to position 3 due to steric effects. Now about 6-membered heterocyclic compounds. An example of heteroatom of the second type is the nitrogen atom in pyridine, which is linked by covalent bonds to only 2 carbon atoms. Pyridine also has a p electron sextet, but the nitrogen atom contributes only 1 electron to it, 1 additional electron being contributed by each of the 5 carbon atoms in the ring. And in particular, the unshared electron pair of the nitrogen atom is not involved. Moreover, because nitrogen's attraction for electrons is electronegativity is greater than that of carbon, electrons tend to move forward the nitrogen atom rather than away from it, as in Pyrrol. Quite general heteroatoms may be referred to as Pyrrol-like or pyridine-like, depending on whether they fall into the first or second class described above. The Pyrrol-like heteroatoms, Nr, R being hydrogen or a hydrocarbon group, and NO and sulfur tend to donate electrons into the p electron system, whereas the pyridine-like heteroatom nitrogen plus R, and oxygen plus and sulfur plus tend to attract the p electrons of a double bond. In 6-membered heteroatomic heteroaromatic rings, the heteroatoms, usually nitrogen, are pyridine-like. For example, the compounds pyrimidine, which contains 2 nitrogen atoms, and 4 trizine, which contains 3 nitrogen atoms. And 6-membered heteroaromatic compounds cannot normally contain Pyrrol-like heteroatoms. 5-membered heteroaromatic rings, however, always contain 1 Pyrrol-like nitrogen, oxygen, or sulfur atom, and they may also contain up to 4 pyridine-like heteroatoms. As in the compounds cyphane with 1 sulfur atom, 1,2,4 oxidizole with 1 oxygen atom and 2 nitrogen atoms, and pentazole with 5 nitrogen atoms. With quantitative measurement of aromaticity and even its precise definition has challenged chemists, since German chemist August Kekule formulated the ring structure for benzene in the mid-19th century. Various methods based on energetic, structural, and magnetic criteria have been widely used to measure the aromaticity of carboxylic compounds. All of them, however, are difficult to apply quantitatively to heteroaromatic systems because of complications arising from the presence of heteroatoms. Chemical reactivity can provide a certain qualitative insight into aromaticity. The reactivity of an aromatic compound is affected by the extra stability of the conjugated systems that it contains. The extra stability is determines the tendency of the compounds to react by substitution of hydrogen. A replacement of a singly bonded hydrogen atom with another singly bonded atom or group, rather than by addition of 1 or more atoms to the molecule via the breaking of a double bond, the substitution reaction and addition reaction. In terms of reactivity, therefore, the degree of aromaticity is measured by the relative tendency toward substitution rather than addition. By this criterion, pyridine is more aromatic than furan, but it is difficult to say just how much more aromatic. And examples of heterocyclic compounds, here are 6-membered heterocyclic compounds, 1 heteroatoms. Include to them pyridine, piperidine, and quinoline, and isoquinoline, and acridine. And you see in this slide 6-membered heterocyclic with 2 heteroatoms, and you see example 1,2-diazine pyridine, and 1,3-diazine pyrimidine, and 1,4-diazine pyrroline, and here you see phenolthiazine. And orbital structure of pyridine. These electrons are in an sp2 orbital perpendicular to the p orbitals. Now, pyridine structure and aromaticity. Pyridine is a 6-membered heterocyclic compound with molecular formula C6H5N, and it's obtained from coal tar. It may be formally derived from the structure of benzene through the exchange of the ring carbon for a sp2 hybridized nitrogen. Pyridine is an aromatic compound, however, the nitrogen's lone pair of electrons is an sp2 orbital and orthogonal to the p orbitals of the ring. Therefore, it's not involved in maintaining aromaticity, but it's available to react with protons, as pyridine is basic. And you see here orbital structure of pyridine. This is a p orbital, and these electrons are in an sp2 orbital perpendicular to the p orbital. Now, pyridine structure and aromaticity. Pyridine can be represented as a resonance hybrid of the following structure, and due to the greater electronegativity of nitrogen and relative to carbons, it tends to withdraw the electron density from carbon atoms at position 2, 4, and 6, which therefore acquire partial positive charge, while the nitrogen atoms acquires partial negative charge, while the carbons at position 3 and 5 remain neutral. Now, synthesis of pyridine. It's a common strategy 5 plus 1, and from 1, 5 dicarbon compounds. You see, with ammonia reacted, then oxidizing, then in this reaction formed pyridine. Another example, Bönemann cyclization. Here is a red hot tube, and in this case formed pyridine, and Hanch synthesize, and in this reaction also ethyl acetate with beta decarbonyl reacted, then formed pyridine. Then another form, 4 from Pyrrol, form pyridine. Then 5 by Diels-Alder reaction also form pyridine. Then basicity of pyridine. Pyridine is a weak base since lone pair is in an sp hybrid orbital. It's a conjugate acid aromatic. You see, pyridinium salt pKa is equal to 5.2. It undergoes many reactions typical of amines, such as reaction with bronzed acids, such as chromic acid and hydrobromic acid. Then the basicity of pyridine reaction compared to Pyrrol. Pyridine is a much stronger base. This is due to the nitrogen lone pair on the nitrogen atom is already involved in Pyr, is not involved in maintaining the aromaticity, thus it free for protonation. However, in Pyrrol, along the aromatic array of p electrons, protonation of Pyrrol on nitrogen atom results in a loss of aromaticity and is therefore unfavorable. And pKa is equal to minus 3.8 compared to imidazole. Pyridine is less basic. This is due to the on protonation the plus V charge can be delocalized over 2 nitrogen atoms, while in case of pyridine it's delocalized over the ring, which interrupt aromaticity. Then compared to analogs aliphatic amines, pyridine is less basic. This is due to the nitrogen atom is pyridine is sp2 hybridized, then more electronegative, and the lone pair of electrons occupies on sp2 orbital, thus it's held more tightly by the nucleus, then the lone pair of electron in aliphatic amines with sp3 hybridides and nitrogen atom, and the lone pair of electrons occupies on 3 sp3 orbital, less electronegative. And you see here decreasing order of basicity. Now, chemical properties of electrophilic substitution. The negative pole in a pyridine ring is at nitrogen, while the positive pole is at carbon scalation, which is opposite to what happens in Pyrrol. This is due to the aerator electronegativity of nitrogen, and relative to carbons, it tends to withdraw the electron density from carbon atoms at position 2, 4, and 6, which therefore acquire partial positive charge, while the nitrogen atom acquires partial negative charge, and the carbons at positions 3 and 5, beta position, remains neutral. Therefore, these positions are the most preferred for electrophilic attack. And also, as a consequence of electron deficiency of pyridine ring, pyridine is less reactive towards electrophiles than Pyrrol, and benzene it resembles highly deactivated benzene derivatives, where it doesn't undergo Friedel-Crafts alkylation or acylation or coupling with diazonium salts. Moreover, electrophilic substitution reactions of pyridine require very harsh conditions, high temperature to take place, and are low yielding. As a tertiary amine, pyridine has nucleophilic properties, thus its reaction with electrophile, say, and nucleophilic substitution on carbon. Pyridine is very reactive towards nucleophiles than benzene. It resembles benzene, having strong, and due to the withdrawing effect of the electronegative nitrogen atom, as apart from the canonical structure of pyridine position 2, 4, and 6 carry partial positive charge. Thus, a nucleophilic substitution proceeds readily at the 2 position, followed by 4 position, but not at the 3 position. Additionally, attack at position 2, 4, and 6 results in a resonance structure in which the negative charge is delocalized at the nitrogen. Thus, it's more preferred, while attack at position 3 or 5 results in resonance structures in which the negative charge is delocalized over carbon only. And orientation of nucleophilic substitution on pyridine, you see, attack at carbon 2 more preferred with charge on nitrogen, then attack at carbon 4 more preferred and with charge on nitrogen, then here attack at carbon 3 charge on carbon only. And next slide, nucleophilic substitution reaction, the Chichi-Bobin reaction. It's Chichi-Bobin reaction, and R can be ortho, meta, and or para substituent. Then reaction with organometallic compounds, lithium reagents, and by lithium we can form these 2 butyl pyridine we can form. Then nucleophilic substitution reactions, third reaction with potassium hydroxide, pyridine reacted with potassium hydroxide, and two pyridone form, and reaction carried out with potassium hydroxide and at 320 degrees Celsius. Then four reduction reactions. Pyridine reacted with hydrogen, nickel, and then formed pyridine. Then reacted these structures formed 1,2 dihydropyridine. Then reacted sodium or ammonia. Then it's a Birch reduction and formed 1,4 dihydropyridine, and etc. Then a derivative of pyridine, nitrogen oxide pyridine or N-oxide pyridine. Pyridine can be oxidized easily to N-oxide pyridine by peroxides. And on the basis of dipole moment studies, N-oxide pyridine is considered as a resonance hybrid of the following structure. The charge appear at position 2, 4, thus active towards electrophile plus, and the plus V charge appear positions 2, 4, thus active towards nucleophiles. As appears from the previous canonical forms, there are positive and negative charge at position 2 and 4. This nitrogen oxide pyridine is more activated for electrophilic and nucleophilic attack at these positions than pyridine itself. N-oxide pyridines are very important intermediates for preparing pyridine derivatives that are difficult to prepare due to the easiness of removal of oxygen atom by reduction. For instance, nitration of pyridine is very difficult and a low-yielding reaction as it occurs at position 3. However, using an oxide pyridine will direct the nitration to position 4, and then the oxygen can be easily removed by reduction as shown in the following scheme, like this. Reaction of N-oxide pyridine, you see. Now, here you see bicyclic heterocycles, and they include in this group purine and pyridine. Here is two bicyclic heterocycles, you see. And 5-membered heterocycles with 2 heteroatoms. Imidazole is an amphoteric compound. The nitrogen atom to which hydrogen is bonded easily liberates proton acid. Unshared electron pair on the other nitrogen is available for protonation base. The imidazole skeleton is present at amino acid histidine. Decarboxylation of histidine gives histamine, a toxic substance which is the reason of allergic hypersensitivity. And you see in this slide 5-membered heterocyclic compounds with 2 heteroatoms, and histidine, histamine, imidazole, and 2-benzimidazole shows a hypotensive activity. And you see this imidazole structure, these electrons are in an sp2 orbital perpendicular to the p orbital, and these electrons are part of the p cloud. Then a pharmaceutical preparation of a pyrazole series, antipyrine, imidopyrin, and analgin express febrifugal and sedative activities and can be obtained by the reaction of ethyl ester of acetoacetic acid with phenylhydrazine. And you see this reaction. Analgin is sulfur derivative of imidopyrin, and oxazole, thiazole, and thiazolidine are constituents of vitamins, coenzyme, and antibiotics. And in this structure you see analgin structure. Derivatives of some 5-membered heterocycles with 3 and 4 heteroatoms and syndones and tetrazole are stimulants of nervous system. Now 6-membered heterocycles with 1 heteroatoms. Pyridine is a poisonous liquid with a bad smell and was found in coal. The most important derivatives are nicotinic beta and isonicotinic gamma acids. Antinicotinic acid, isonicotinic acid. Nicotinamide, vitamin B, PP, and its N-diethylamide, codamine are well-known drugs. And you see cardamine, which preparation of cardamine and nicotinamide reaction. Then hydrazide of isonicotinic acid, tubazide, and its N-substituted derivative, phtivazide, are effective antituberculosic drugs. And you see this reaction, preparation reaction of tubazide and phtivazide. Then some substances with pyridine, quinoline, and isoquinoline rings are illustrated below. And papaverine is used as antispasmodic drugs. And 8-hydroxy-5 nitroquinoline, it's nitroxaline, is an antibacterial drug, especially at kidney infections. 8-hydroxy-7 iodine 5 chlorine quinoline is effective at bowel infection. Then 6-membered heterocycles with 2 heteroatoms. Hydroxy and amino derivatives of 1,3-diazine-pyrimidine, uracil, thymine, and cytosine as constituents of nucleic acid illustrated in tautomeric forms have a special importance. And you see dioxyform, lactin form, and lactone form of uracil. Then here is thymine with 2,4-hydroxy-5 methylpyrimidine and 5-methyluracil form. And you see here cytosine, you can also say 4-amine 2-hydroxypyrimidine. Lactam or oxoforms predominate in equilibrium and occurring nucleic acid molecules. Pyrimidine derivatives, barbiturates, are pharmaceuticals with sedative, hypnotic, and anesthetic properties. They may be prepared from substituted malonic esters and urea and form barbiturate. Examples include phenobarbital, R1 is equal to acyl, R2 phenyl, nembutal R1 is equal to acyl, R2 is equal to 2-pentyl, and secanyl R1 is equal to allyl, R2 is equal to 2-pentyl. Sodium pentothal used to induce general anesthesia by intravenous injection is a thiobarbiturate with the same structure is nembutal, except that the urea oxygen is replaced by sulfur. And pyrimidine with an entirely different type of activity is thiamine or vitamin B1, a coenzyme required for certain metabolic processes and essential to life. And the structure of vitamin B1, another name thiamine. Phenothiazine is sulfur and nitrogen containing heterocycle 2-10. The substituting phenothiazine is widely used in psychiatry as drug, aminazine. And you see structure. And bicyclic heterocycles. Pyrrole is bicyclic heterocycle formed by condensation of pyrimidine and imidazole rings. Amino and hydroxyl containing pyrines, adenine and guanine are the constituents of nucleic acid. Hypoxanthine, xanthine and uric acids are the production of nucleic acids. And you see, uric acid is product of purine metabolism. About 1 gram of uric acid is excreted with urea every day. Salts of uric acid urates deposit at joints and kidneys at podagra. Uric acid and sodium urate. And pyridine is a constituent of folic acid in form of 2-amine 6-methyl 1,4-oxidative. And here's pyridine is a constituent of folic acid in form of 2-amine 6-methyl 4-oxidative, and riboflavin as 2,4-deoxyderivative. Another name is vitamin B2. Now about alkaloids. Alkaloids, heterocyclic, nitrogen-containing plant materials with pharmacological properties are called alkaloids. Over 5,000 alkaloids are known. Pyrene alkaloids, coffein, theophylline, and theobromine are nitrogen methylated derivatives of xanthine. They occur in tea, coffee, and cacao beans. Now about classification of alkaloids. Alkaloids classified through typical alkaloids that are derived from amino acids and have a nitrogen in a heterocyclic ring, for example, atropine. Then protoalkaloids that are derived from amino acids and do not have nitrogen in heterocyclic ring, like ephedrine. Then pseudo-alkaloids that are not derived from amino acids but have nitrogen in a heterocyclic rings, for example, k.e.n. And false alkaloids are non-alkaloids give false positive reaction with alkaloidal reagents. And you see in this slide heterocyclic alkaloids type, and here's 14 types of heterocyclic alkaloids. You see pyrrole and pyrrolidine, pyrrolizidine, pyridine and piperidine, tropane, quinoline, isoquinoline, and apopropyne, and quinolizidine, indole or benzopyrrole, indolizidine, imidazole or glyoxaline, purine, pyrimidine, imidazole, and steroidal, some combined as glycosides and terpenoid. And you see in this here structure of pyridine, and pyridine, then pyrrolizidine, and quinolizidine, etc. Now about imidazole. Imidazole is an organic compound with the formula C3H4N2. This aromatic heterocyclic is classified as an alkaloid. Imidazole refers to the parent compound, whereas imidazoles are a class of heterocycles with a similar ring structure but varying substituent. And imidazole was first synthesized by Heinrich de Baz in 1858, but various imidazole derivatives had been discovered as early as the 1840 century. These syntheses, as shown below, use glycol and formaldehyde in ammonia to form imidazole. These syntheses, while producing relatively low yields, is still used for creating carbon substituting imidazole. In one microwave modification, the reactions are benzyl, formaldehyde, and ammonia in a glacial acetic acid forming 2, 4, and 5 triphenylimidazole. It's another name Lofin. And the uses of esters. Caffeine is an example of a class of compounds called alkaloids, which are produced by plants, and it consists of C8, H10, and nitrogen 4, oxygen 2. The name alkaloid means alkali-like, where alkali is a base and hence refers to these basic properties. Carry out the experiment to extract caffeine from tea. And alkaloids chemistry. Sertumer in 1806 laid the foundation of alkaloids chemistry. It's a branch of pharmaphytochemistry, which deals with the study of alkaloids. He reported isolation of morphine from opium. What's alkaloids? Alkaloids mean alkali-likes. The pharmacist Masons proposed the term alkaloids in 1819 year, and alkali is equal to base oid-like sub are basic nitrogens compounds of plant origin which have a complex molecule structure and many pharmacological activity. Landenberg alkaloids are defined as natural plant compounds that have a basic character and contain at least one nitrogen atom in a heterocyclic ring and having biological activities. And characteristic features alkaloids are basic nitrogenous plant origin, mostly optical active, and possessing nitrogen heterocycles as 3 structural units with physiological action. And occurs isoquinoline formula you see here, and emitting the principal alkaloids of ipecac ground roots of Uragoga, ipecacuanha, and here's licorin from the bulbs of Narcissus and Amirals. And emetin is a drug used as both on anti-protozoal and induce vomiting. and it's a toxic crystalline alkaloid. It inhibits protein synthesis and maybe inhibit ascorbic acid biosynthesis. It serves some interest in the study of certain yeasts. And you see here caffeine, 137 trimethylxanthine, and theophylline is 1,3-dimethylxanthine, and theobromine 3,7-dimethylxanthine, and nicotine, anabasine, and k.e.n, lobeline, pyridine and pyridine alkaloids. Now, nicotine is a toxic vasoconstrictor, and it occurs in tobacco livers. Lobeline stimulates respiration. Anabasine and k.e.n are high toxic. Cocaine and atropine are derivatives of bicyclic alkaloid tropane constituted of pyrrolidine and piperidine cycles. Quinoline and isoquinoline cycles are present in the molecules of antimalarial drug quinine, anticonvulsant, papaverine, morphine, and codeine. Now about antibiotics. Antibiotics discovery is one of the greatest triumphs of medicine of 20th century. In 1929, Fleming discovered that mold produces a substance lethal to the bacterium Staphylococcus aureus. Later, Chain and Florey isolated and determined a substance responsible for antibiotic activity. It was beta-lactam or cyclic amide with 4 membered rings. The well-known semisynthetic antibiotics were prepared by an acylation of 6-aminopenicillin acid. And the classification of antibiotic based on chemical structure for sulfonamides or sulfadiazine and quinolones, ciprofloxacin, nalidic acid, then tetracyclines, doxycyclines, tetracyclines, aminoglucosides, and gentamicin, streptomycin, then macrolides, erythromycin, roxythromycin, and azithromycin, then beta-lactam antibiotic penicillins and cephalosporin. Then antibiotic interferes with cellular and processes and kills bacteria. Penicillin interferes with the synthesis of the cell wall. Tetracycline interferes with protein synthesis. Bacteria can mutate and become antibiotic resistant. Now, you see in the slide, antibiotic penicillin acids, acyl derivatives of 6-aminopenicillin acids, and benzylpenicillin G, penicillin V, and ampicillin formula, then amoxicillin formula. Then the discovery of penicillin led to a widespread search for other antibiotics. Cephalosporins were isolated from sewage. They have a broader range antimicrobial activities than penicillins. And the family of tetracyclines has 4 rings. They are antibiotics of broad spectrum. And chloramphenicol is a synthetic antibiotic of aminodiol series. You see structure. And our lecture finished. Thanks for watching and attention. Bye.